Something I just realized before the break was, right as the break was out, is that, this formula kind of looks wrong for summation by parts, integration by parts. If you recall, it's uv minus v du. Yeah, so this really should be a plus, and this should be a minus. But do you see that this is uv, right? Evaluated at the endpoints q and p. Q is bigger than p. And this is minus v du, and the reason it's minus v du is because it's really minus du. If u is b, then du should be bn plus 1 minus bn. So that's where the sign comes from. Okay. Good. So let's resume. I'm going to mention just one more thing about products of series. Yeah, actually, I'll just mention it now. This is good. So if you want to take sums of series, we know what it means to take the sum of series. You just sum term by term, right? So for instance, if I want to add an plus the sum of bn, that's the sum an plus bn. That's what I mean by the sum of the series. But a question you might ask is, what do we mean by the product of a series? Products. What does it mean to take the product of two series? So what do you think we might mean by taking the product of two series? Well, it's not sum of a and bn. That's what you might think of as being a product. It's not the natural way to define a product. So let me mention that if you have two series, the product is actually defined slightly differently than you would think. So let me give you the motivation, and then you'll see where the definition comes from. So the motivation actually comes from power series. So in power series, you might have a series that starts off like this: a naught plus a1z plus a2z squared plus dot dot dot. And you might have a second series, b naught plus b1z plus b2z squared dot dot dot. Yeah? And if you ask somebody to take the product of these two series, what would you get? What's the first term? A naught, B naught. Okay. What's the second term? It has a single z in it, right? So it comes from a term here and a term here. So that's either a1z, B naught, or a naught, B1z, yes? So the second term here is actually a1, B naught plus a naught, B1 times z. Yes? And the third term is three terms, and it either comes from a2, B naught, or a1, B1, or a naught, B2. Okay? Steve's happy with that. And Maya probably can see the general pattern, which we won't write out. Dot, dot, dot. That's a good way to write the general pattern. Love that. Yeah. So in fact, with this motivation, here's how we define the product series is you'll let Cn be the sum of ak b sub n minus k, and k goes from 0 to n. And so the product series is defined to be, it's the sum of Cn's. Okay? It's not exactly what you would think of at first as a natural notion of a product series. Okay, now that is cool. I want to save that picture. Here's the other thing. The reason this is a product series and not the thing you might think of, a n, b n. If you have a series, sum of a n that converges to big A, and sum of bn that converges to big B, this series, sum of AN, BN, won't converge to big A, big B. It won't converge to the product of these two, the things these converge to. So this is not a good notion of a product. Yeah? But this one does under certain situations, okay? We just want to be a little careful there. So I'll just write this down. So one problem is the sum of Cn may not converge, even if the sum of AN and sum of BN do. Okay? But here's a theorem. You can say that it turns out if sum of AN and the sum of BN converge absolutely, I haven't said what that means yet, but we will in just a second, then the sum of Cn converges, the product series converges. Not only that, but if these converge absolutely, and they converge to A, big A and big B, then this series converges, and it converges to, take a guess, AB. Okay? Not necessarily. Good question. I'm not sure. But it converges to big A, big B. Yes?
When you say product series, is that actually just the sum of the CNs, or is it the sum of C and Z to the n?
No, it's just sum of the CNs. Yeah, so I'm just saying this is the motivation, where the power series here, of course, is the terms are AN Z to the n, BN Z to the n. Then the product series would be AN, CN Z to the n. But if the power series, if the series is just sum of AN, sum of BN, then the product series is defined to be sum of CN. Okay, good question. Yes? Oh, we haven't defined it. I'm just I'm motivating that, hey, you know, there's a concept here that's going to be helpful for us. Okay, so we're about to define this. Okay. Okay, I'm not going to prove this. I'm more interested that you realize that there are theorems that deal with it. There are actually a couple of theorems in the book that talk about product series and conditions in which they converge. So I encourage you to look at them, but just be aware that there are conditions under which these things converge. And this motivates the concept of absolute convergence. So absolute convergence is basically a kind of convergence where you look at absolute values, right? So we're going to define this. We'll say a series with, you know, maybe positive or negative terms converges absolutely if the associated series with absolute values converges. That's what absolute convergence means. So an example would be an alternating sum of reciprocals. Does this converge absolutely? By the way, does this converge? Yes, it's an alternating sum of terms that go to 0 and are decreasing and go to 0. So this actually converges, but not absolutely. Because its absolute series is going to be the harmonic series, not absolutely. Okay. Now, a cool theorem is that if a series converges absolutely, then it converges. So if it converges